All right, so we're continuing with entanglement theory, and in particular, we're going to be talking about an entanglement measure called squash entanglement. I said last time we might talk about squash entanglement and relative entropy of entanglement, but there's not enough time. We would need another lecture for relative entropy of entanglement. So I personally favor squash entanglement, so we'll talk about that. Maybe I'll be able to mention why. Okay. So let's motivate it a bit. Okay, we'll motivate squash entanglement. What I want to first do we're going to first go down kind of a wrong path, but it'll get us towards the right path. Okay, so maybe that'll be interesting. So we're going to look at a measure we've already looked at. Okay, so this will be a measure of a bipartite state, rho AB. Okay, so we're going to take. Sometimes people think of relative entropy as being like a distance, but it's not a formal mathematical distance because it doesn't have a triangle inequality. It's asymmetric. Right? It's not symmetric. And but still, we'll think of it this way. So we'll take the relative entropy to the set of product states. Okay, so tau A and sigma B are states. We're going to take the infimum of the relative entropy with respect to all these states. And this is the relative entropy to the set of product states. Okay? And one thing that you did in a homework exercise is you proved that this is equal to mutual information of the state rho AB. Okay? So it's the minimum relative entropy of product states. Okay. What do we know about mutual information? It's non-negative and it's equal to 0 if and only if rho AB is a product state. That is, it can be, and if it's a product state, it can be written as the product of its marginals because it's already a product state. Okay. This is a correlation measure. Okay. Or measure of lack of independence or lack of productless state. Okay. And what is not good about this is that it's strictly non-zero for separable states that cannot be written as a product state. Right? But the way that the kind of hierarchy goes is there's product states, and there's separable states, and then there's the all bipartite states. Right? And I really shouldn't draw this. Probably put like ears on it or something like this because it's not a convex set. Okay, it's like a silly joke. All right, but it's not a convex set. I don't know if it looks like that, but it's not a convex set. That's the point. Okay. So what did we say last time in our abstract exposition of entanglement measures? We said if it's an LOCC, the main requirement is that an entanglement measure is an LOCC monotone. It does not increase under LOCC. And then as a consequence of that, we proved that it takes its minimum value on the set of separable states. Okay. So that's another reason that this is not a good, this is not an entanglement measure, is because it takes its minimum value on product states and not on separable states. Okay. But what we're going to do, and then furthermore, mutual information can increase under LOCC. Right. You can go from a product state, which has 0 mutual information, do LOCC, get a separable state, which has non-zero mutual information. So this on its own is no good, but we can work with it a bit. We can massage it a bit to get a nice entanglement measure. Right? So just write this. MI is not an entanglement measure. Okay. So how can we use it? So suppose that your sigma AB is abbreviated like this. It's a separable state. It's in the set of separable states. So what does that mean? I guess we've been talking about this for a while. It can be written as a convex combination of product states. Okay, and then, we think of this state being created by this kind of Markov process, where in the background, a classical variable x is generated, and then conditioned on that, states in A and B are generated. Okay, and for Markov processes, you have like conditional independence. Right, so that suggests that rather than using mutual information, we could use conditional mutual information. It's an interesting way to get an entanglement measure. Okay. So what do we first do? Let's draw out this hidden variable from the background and make an extension state. So this state is extended by sigma ABX. So we'll make an explicit classical system for this hidden variable in the background. Okay, so there it is. And then, if you were to look at a convex combination of mutual information of these states, this is equal to 0, right? Because the mutual information of each of these product states is 0. The convex combination is 0 as well. So this is 0. The one thing you can show, and I don't know if we did it explicitly in the lectures. It's probably in the homework, or it's in the books. This is equal to, for a classical system X, a convex combination of mutual information is equal to conditional mutual information. Okay, that's true for the classical case, but not the case. We don't know how to do that fully quantum. But this we can do. Okay. So that we can do. And maybe I'll just give you a quick reminder of the definition of conditional mutual information. It's going to be this. And then there's another way you can write it in terms of conditional entropy. It's like you remember the definition of mutual information is the sum of the individual entropies minus the joint entropy, but then condition. Okay. those are all things you can do, but this is the key quantity we'll work with. So that's great. It has the desired property that it's equal to, so that we know conditional mutual information is always non-negative. Even if X were a quantum system, we know for any tripartite state, conditional mutual information is non-negative. That's called Strong's additivity of entropy. We talked about that a few weeks ago. Okay, so it's always greater than or equal to 0, and then you see it's taking its minimum value on a separable state. So it at least has that necessary property. Okay, and what we'll do is we're gonna do another step, and then we'll get to squash entanglement. Okay, so a potential measure of entanglement is this. Taking an infimum. So what did we do here? We took a separable state. We took the hidden classical variables. We brought it to the forefront in this classical system, and then we evaluated the mutual information, the conditional mutual information. Okay, but there's something important to keep in mind. So there are different decompositions of a separable state, some of which might not be as a tensor product of states. Okay, so for example, if we have the maximally mixed state, identity over 2, this is for qubits, right? This you could write, so this is already in product form, okay? However, you could write it as a uniform mixture of Bell states. Right? The Bell states form an orthonormal basis. And so you can write this as a uniform mixture of the Bell states. We defined those previously. They're related to each other locally by Pauli rotations. Right? So each of these is entangled. And then this is decomposition where if you were to evaluate the conditional mutual information, so you put a classical variable in the background, each of these has mutual information of 2. And so if you took this decomposition, that would be a bad decomposition. And you would get a value of 2. And so that's why we're doing this. We're going to do an inf, an infimum of the conditional mutual information over all extensions of the original state row right? So this is the, implicitly this is over states, okay? And we're making X classical for now, okay? And this is the extension property. When you trace over X, you get back the original state. So this is a function. This is actually called classical squash entanglement. We don't do that in the book, but all right. So you're measuring the entanglement between the systems A and B of the state row. It's called classical squash entanglement because the extension system is classical. Okay, and then it has the property that it's 0 if the state's separable by exactly this argument. Right? If the state row is separable, then there exists an extension of this form such that when you evaluate the conditional mutual information, you get the minimum value of 0. Okay? So that's the basic idea behind squash entanglement. This itself is an entanglement measure. And it's actually easy to prove that it's faithful. Okay, what does faithful mean? It's equal to 0 if and only if the state's separable. Right? So why can we say that? Well, when the conditioning system is classical, you can write it like this. And if it's 0, that means these are all non-negative numbers. This is non-negative as well. So the overall thing is 0. That means that each of these is 0. And the mutual information is 0 if and only if it's product state. So that immediately implies the faithfulness, right? If the measure is 0, then there exists an extension system such that each element of this ensemble in the sequential state is equal to 0. It is a product state. Yes.
What are the subscripts?
This right here, CL is for classical and SQ is for squash. We'll explain in a minute why this funny name squash was chosen. I think in a previous lecture we kind of discussed it, but we'll return to it. Okay, and you can actually prove that this is an entanglement measure. Okay, however, there's a better one for applications. The most notable application of squash entanglement is that it's an upper bound on an operational quantity called distillable entanglement, which is the rate at which you can distill maximally entangled states from a given bipartite state using LSC. Why do you want maximally entangled states? Well, they're good for dense coding and teleportation and quantitation. Okay. So, what is the definition of squash entanglement? So let's go one step further. So that's just going to be, so E squash will be so now it's just SQ for squash, right? And the main thing will be, don't take a classical extension system. Why restrict it to be classical? Just make it an arbitrary quantum system. Okay? And that's the basic idea.
That should make the quality more difficult to compute, right?
Yeah, that's a very good point, and it's not known whether it's computable. So that's a great open question in quantum information theory that is not been addressed, but it's useful as an upper bound on distillable entanglement. And then what you do is you pick any old extension, and if you can be clever, you pick a good extension, you can get a good upper bound. Okay. So but yeah, that's a very good point. But there's also a pre-factor of 1/2 in front. The definition is precisely the same, except we use the notation E instead of X. You know, it's a general quantum extension. Okay. So to address the very good point that you're making, if we define, so distillable entanglement is something we can define operationally. Okay. It's in words. It's the maximum rate in which we can distill E bits from many copies of rho AB using LOCC, such that in the limit, the error goes to 0. That's in words. Okay. And then what can be shown is this upper bound. Okay. So that's a nice application of squash entanglement. And then if you're interested in an upper bound on distillable entanglement, you're then free to choose this extension system in a clever way, right? And so if you choose some extension, you can prove, oh, you know, this is less than that for some choice of an extension. And so, you know, we've written several papers about this kind of thing. Other groups have as well. But, you know, it's not known whether this is computable. It's not known whether this precisely with the theme is computable. What's the reason for it? There's no bound that's known on the size of the dimension system. It's the size of the extension. There's no bound on the dimension that's known. It could be you actually have to take a sequence of systems that get larger and larger and larger, even if A and B are finite dimensions. With this one, there's a bound that's known. It's related to the dimension. I forget what it is, but it's related to the dimension.
There is a bound.
If the extent, if you use this definition, this is not squash entangled. This is called classical squash entangled.
What do you mean by a bound that between?
So this, in this case, the infimum can be replaced by a minimum. Okay. We have to minimize in a set of states where the system X is somehow related to the dimensions of A. Maybe it's a product of the square of. Yeah, I know what it is. Okay. But for this one, no bound is known. That's been one of the great open questions in quantum information theory since 2003. So, yeah, if I had to guess, I would guess that it's not computable. It's just kind of a feeling. Okay, so why is it interesting and useful? Well, it possesses many desirable properties of an entanglement measure. Okay, so it's something you can work with analytically in a number of situations. I should say it has its roots. There's a researcher at ETH Zurich in classical information theory. His last name is Maurer. Came up with a measure called intrinsic information and used it to bound rates of secret key distillation from classical tripartite probability distributions, where one system corresponds to, two of the systems correspond to honest parties, Alice and Bob. The third corresponds to eavesdropper. So it has these cryptographic roots, and that's why it's called squash entanglement. It has that root. I guess wanted a different name. And you can think of it as like there's a state, the original state Alice and Bob possess, right? And then, in principle, there could be a third system in possession of an eavesdropper, okay? And this is measuring the correlations between Alice and Bob from the perspective of the eavesdropper, okay? And so it's like the eavesdropper is doing something to reduce the correlations between Alice and Bob as much as possible, squash them down. So that's where the name came from. Okay. Subsequently, someone came up with a measure called the poofed entanglement, but that was not as popular. So, I think it just reduced the local entropy of the states. But anyway, good. So that's the definition. Let's start proving some things about it. So it's non-negative, right? Why is that? There's some strong subadditivity of entropy. That we already proved. That holds true for all tripartite states. So, it implies that the measure is greater than or equal to 0. So that's good. Next, it's faithful. Okay, so how does one way of this go? Well, that was how we motivated the whole measure, right? So if rho AB is separable, you can pick this extension system to be classical. You can pick it to be exactly like this. And then, that implies it'll be equal to 0 if the state's separable. So that's how we motivated the measure. The opposite implication is much more challenging. We won't do that. I think we provide references in the book. Okay. Okay. Another one is convexity. And with squash entanglement, all the proofs of the properties just boil down to kind of simple information identities. Okay. In particular, using the chain rule for mutual information, for conditional mutual information, which we already learned about. And that's kind of it, just really using the chain rule. Okay. So let's prove convexity. Maybe I'll state the question. So like getting formulas for this for bosonic Gaussian states, I consider that a great question. Some people have attempted that. If you were trying to evaluate this for a bosonic Gaussian state, I think that would be an interesting question. Yeah. Bosonic Gaussian state, fermionic Gaussian state, that kind of thing. Maybe special classes of states you could get a formula. So there's been some work on that, but there's no definitive answer. Okay, convexity. So what is that? This is going to be like an average state. It's less than the average squash entanglement. Okay, so rho bar AB is a mixture of these. Okay. And remember, we said that if an entanglement measure obeys this property of invariance under classical communication, then convexity is equivalent to saying that entanglement is reduced under the loss of classical information that identifies which state it is. Right? You kind of see that here, right? Like this product state is a mixture of Bell states, right? So each of these will have a squash entanglement of 1 with a normalization factor of 1/2. And then the product state is squash entanglement of 0. So convexity, that's a way to think about convexity. Like this product state arises from losing which, you don't know which state it is in the ensemble. So
I am confused because entanglement should be the same if you look at the left-hand side or the right-hand side, right? State.
oh, I'm sorry. I guess I was saying, so let's apply this inequality to this example, right? This right here is the mixture of the 4 states. The mixture has entanglement 0. Then the average entanglement of each individual state, the entanglement of this state is, squash entanglement is 1, 1, 1, 1, and then the average entanglement will be 1. So that's what I'm saying. Okay, so let's prove convexity. And a lot of these proofs just amount to figuring out how to choose the extension system. So we'll let omega ABE X extend rho ABX. Okay. Then, if we embed these states in a classical quantum state, that will be an extension of this one. So rho AB bar. Okay, why is an extension? Sorry, then this state extends rho AB bar. So why is it an extension? Well, extension systems are X and E. So if you trace out X, you get this mixture. If you trace out E, you get this mixture. Because we said from the beginning that omega X AB extends rho AB bar. Okay. So now with that, what does this mean? take twice the squash entanglement. Put in the factor of 2 there because we want to get rid of this normalization factor. Now, using the definition, let's call this state omega ABE. Okay. So this is as we said, this is a particular extension of rho AB bar. Then we can do this. Okay. But one thing we used over here, if you have a classical system in the conditioning part, then you can write a convex combination of conditioners information. So because this x is here, something you can prove is that this is equal to so, and then that's kind of it for the proof. Why is that? Well, this omega x is an arbitrary extension of rho ABX. Okay? And so if it's arbitrary, that implies that this inequality will hold when taking in femum over omega x. Okay? So then, you know, implies star because arbitrary. Extension of rho AB. Okay. So good. Now let's prove that it's additive. Proving that it's additive is useful for getting this upper bound of the stowable entanglement. We'll return to that later. Okay. We'll call it super. So we'll make a statement about superadditivity, and then we'll make a statement about additivity. That's why I put the super in parentheses. So for a state rho A1, A2, A1, A2. So this kind of state, you should think of in terms of this diagram. So it's like Alice has 2 systems, Bob has 2 systems. And we want to know like how the total squash entanglement is related to the individual squash entanglement of A1, B1, and the individual squash entanglement of A2, B2. Okay. So we can prove that there's like a superadditivity inequality. So this is greater than, yeah, indeed you can use this overused expression, greater than the sum of the parts. That's superadditivity. So squash entanglement of Alice's systems together, bunch together, you know, and then entanglement across this cut with Bob's systems together, it's greater than the individual squash entanglements. Okay. Why is that true? Chain rule. Let's prove it. So omega A1, A2. This will be an extension of rho. I won't write all the systems. Okay. Then we use the chain rule for conditional mutual information. So from the definition of squash entanglement, right, it's like conditional mutual information of whatever Alice has with whatever Bob has from the perspective of the eavesdropper or extending system. Okay, so in this case, whatever Bob has is A1, A2. Sorry, whatever Alice has is A1, A2. Whatever Bob has is B1, B2. Okay? But now using the chain rule, we can break this up into different sums. Okay, so we'll apply the chain rule twice. First, like this. So we can think of the correlations between Alice and Bob as being built up in steps. First, we look at the correlation between A1 and the Bobs plus A2 and the Bobs. And now, whatever you already built up is there on the side. Okay, so that's like, I don't know, that's how I think of the chain rule. It's like the correlations get built up in these steps. And whatever you built up in the first step is there on the side for the second step. Okay. But now we can apply this again. So now we'll build up Bob's correlations with Alice, and these correlations with Alice too. Do that, each of them in 2 steps, right? So in the first step, we'll look at Bob 1 with A1. And then in the second step, Bob 2. Okay. And now we'll do the same thing here. That's the chain rule being applied successively. Okay. And then what do you notice? The desired inequality is about A1, B1, and A2, B2. So here's, conditional mutual information between A1, B1, and E, and A2 and B2 given these elements.
Why do you keep A1 in the second summons, but you don't keep A2 in the first? Second.
Sorry, which one? This one?
So if you go to the first equality,
This
right, why there is no A2 multiplied E? Analogy was.
Oh, because I decided to do A1 first. There's another, like, you could also do the chain rule in the opposite way. You could do A2 first and then A1 condition on A2. Is that what you're asking?
Yes.
You could do it the other way. So I made a choice. Actually, when we're doing this, I realize we get an inequality stronger than this. But okay, so is the answer? Is your question?
Yes.
Second, B1. The second.
Oh, that's-
On the right side.
let me revisit this. Ah, okay. Why did I draw students? Oh wait. Okay, we're doing Bob here. So Bob with A1. Then okay. So you're saying right here, right? Is that right?
But
No, A1 should not be there. A1. That's it, right? Okay, good. Thank you. Is that your question? All right. And everything else is fine. All right. So actually could simply drop cross terms, but I'm actually, we can do something stronger. Why don't we just do the stronger thing? Okay, so the squash entanglement involves an infimum over all extensions, right? So E, so we chose this state to extend row A1, A2, B1, B2. But now we're interested in the squash entanglement between A1 and B1. And so we get A1 and B1 by tracing over A2 and B2. And then, you know, if we trace over A2 and B2 of this state, then E is a system that extends A1 and B1. Okay? So that's a legitimate choice of an extension for the squash entanglement. And then you get this, squash. And actually what's usually done is that these terms are then dropped, but we can see that you get a stronger inequality by keeping them. So why don't we just keep them? Does that make sense? So it's like the squash entanglement is larger than the total squash entanglement is larger than the sum of this squash entanglement, this one, and this one, all the possible combinations. So it's kind of interesting. So why don't we just do that? And the argument is the same. E and B1 extend, or a choice of an extension, and with an infimum over all extensions, or small. Squash. 2 row plus B squash. 1. And the first line, we chose an arbitrary extension, omega of rho. And so this inequality has been proven for arbitrary extensions, so then it implies squash. 2, 2, all the combinations. Okay, and then that implies this because squash entanglement is non-negative. All right. So that was just using the chain rule and like breaking up the correlations into different parts. Now what we want to show is something stronger for product states. So suppose that now suppose that rho is a product. Call it mega A1, tensor tau. So what does that mean? This picture now changes. Okay, the picture is that the state now looks like this. Right? And so now the question becomes, well, is this squash entanglement still greater than the sum of the parts, or is it strictly greater, or is it just equal to the individual squash entanglements? And the answer will be that we have additivity, okay, in this situation with the product state. Right? So how do we know that? Well, from superadditivity, we just proved this, but between A1 and B2, if you trace over A2 and B1, A1 and B2 are in a product state. So the squash entanglement is 0. The same for this cross term. That's also 0. So in that case, we'll get E squashed. So the superadditivity implies that. So now we have to prove the opposite inequality. Okay. So this is rho and now negative time. Okay. What about the opposite inequality? Well, it's going to be simple. So at omega A1 B1 extend B1. Now, same for tau, find an arbitrary extension. 2. Okay. Then we take the tensor product of the extensions. This extends the overall state under this assumption of the product state. Right? So then we just roll with it. Use the definition. 2. So we can choose the extension of this product form, right? It's a legitimate choice because the definition involves an infimum. It's going to be less than negative tensor time. Okay. And then one thing you can show, we didn't do this. I guess you'll trust me, it's in the book. If you have a product, the conditional mutual informations will be added to. You'll get a sum. Okay. That you could prove, well, you could prove it using the chain. You can prove it. It's just there. Right. So this will be a sum of this one. What's this one? And then same argument that we made before, right? Omega is an arbitrary, this state is an arbitrary extension of omega, this state is an arbitrary extension of tau. So then we can take infimum and then get the squash. Less than this. Okay. And then, this one, superadditivity together with the subadditivity implies additivity. So I'll just write that. That's the additivity. And that's one of the nicest properties of squash entanglement and this additivity. They're products, kind of a natural thing. Entropy obeys that for product states, like an individual system. And so additivity is something we typically look for. Okay. Now I want to show you that it's an entanglement monotone, that it's actually an entanglement measure. Okay, that it does not increase under LOCC channels. And it'll have the non-increase under selective LOCC monotonicity, which is kind of the more complicated kind of LOCC monotonicity we talked about at the end last time. So that's like at the end of an LOCC procedure, you can create some ensemble, like with some probability to make some bipartite state, with another probability to make a different one. Each state is labeled by a class element. And then the statement we made is that entanglement does not increase on average. Okay. And the lemma we proved is that to prove that, all you have to show is that the quantity is not increasing under local channels and invariant under classical communication. Okay. So right now, unless there are any questions about additivity. Yes.
So, will we make this equality if we include the entanglement of like of the other conditions like A1 with B1, B2? We include like the sparse entanglement in the other conditions.
Oh, all possible partitions.
Yes. Not only like conditions.
You're saying like as
Like
A1,
with
A2, and
B1.
B1. I'm skeptical. I think at that point you could exceed. I'm skeptical because this right here was equality. Like this gives you the partitioning.
Yeah.
It's one possible partitioning. So the kind of thing you're saying is like, oh, this is a partition.
Yeah.
Right? And then what we did was we broke it up. And there's only so many ways you can break it up and still have equality. I'm skeptical whether you can have that, but that's a very interesting question.
Because everything
Maybe like with minus signs, you can do something like, you know, with there are generalizations of like the union bound quality of minus signs. I don't know.
I'm just saying because we took the partition like that, but then we brought it and we left with only pi partitions. But
Yeah.
if at the beginning I add some extra types of mutual information such that at the end I have the other partitions as well, plus the pi partitions.
Yeah. Yeah. There's also multi-partite measures of squash entanglement as well. So recently, Megan and I posted a paper related to that. But throughout the whole book, we're just saying about it. Okay. Sure. Yeah, it's an interesting point. Okay. So it's proved that it's a selective L system all the time. Right. And proof will consist of two parts. So non-increasing under local channels. Through that, we'll again use this wonderful property of conditional mutual information, chain rule. And then the other is invariance under classical commutation. What this is better. Okay, so for the first part, we'll prove that CMI does not increase. It's called LC for local channels. Okay. So what does this mean? I'm going to use these extra Greek symbols, C, theta. So CADE will be a tripartite state. You act on that with the tensor product of channels. That's what makes this is B prime. This is how we'll define zeta. Okay. So this one wants to do the sign. So if we have this holding for all tripartite states, you then automatically get that squash entanglement is not increasing in the local channels. Why is that? Well, you say, okay, zeta is an arbitrary extension of rho AB. Right? And then under local channels, it goes to this. This is the picture. The state here is rho, and the overall state is. Okay. This is the picture corresponding to the discussion we're having. Right. So if we prove that CMI obeys this inequality, then the squash entanglement will as well, because you can start with rho AB, you can start with rho AB, this C is an arbitrary extension, and then the data processing holds, then there's a state, there's a bipartite state of A prime, B prime, extended by this, right? And so then taking an infimum over all extensions, you get squash entanglement. And then we prove that the inequality holds with C, an arbitrary extension of rho AB. So then it'll hold for squash entanglement. That's the same kind of reasoning we've used them throughout the lecture for squash entanglement. Okay, so we have to prove this. For that, we'll just use chain rule. Okay, so we'll let U be an isometric channel that extends the original channel. So this whole lecture is just like extensions everywhere, right? It's a lot of reason and quantum information. So left, right. So now we'll expand this diagram. This. U. Okay. So what is the argument? Well, look at the CMI of the original state, right? This is a local isometric channel. This is a local isometric channel. Conditional mutual information is invariant under local isometric channels. It's just like, you can think of it as like a unitary, it's just like changing how you look at the state, like the kind of the basis or whatever. Right? So this holds. Okay. Now what? Chain rule. So we'll build it up in steps. Hopefully do it correctly. Right. That's the first step. And then in the second step, do the chain rule again. then plus this third term. CMI is non-negative, so we can drop this term and this term. That's the desired inequality. So just using chain rule, and you get it. Good. So we get data processing under local channels. Then we have to do part 2, invariance into classical communication. So what is that? You said it last time, but let's say it again. It's like you have this classical quantum state, and the picture looks like this. You can think of this classical system, the way I drew it, it's like it's with Alice, right? And you can look at the entanglement between these two and this one. And then this could go over here by like classical communication. It could be copied, and so you can end up with a copy over here as well. The point is that the entanglement won't change. Okay? That's the invariance in the classical communication. Squash E equals and then furthermore, this right here, it's almost like a different statement than invariance in the classical communication. You have this convex decomposition. So that's what we want to prove. So how do we do it? Space. Okay, first step. We have the state rho x AB. We append a classical label of that state to either Alice's side or Bob's side. That is a local channel. Okay? We just proved that squash entanglement is non-increasing under local channels. Also, discarding X is a local channel. Okay? So we can append it or discard it, and then because in both cases you get two inequalities. When you append, you'll get one inequality. When you discard, you get the other. Then you get equality. Okay? So you can say that E squash X A B with respect to this state. Right? So why don't we give a name to this? Let's call it a tau X. Tau. This is the same as and we should probably call it usually enough. Put a label X because it depends on the actual label X, right? Tau X. And that's because, just to say it again, like, we have this squash entanglement. We can append this X, right? And then it goes down. It doesn't increase. So you have one inequality. That's right. It's this one. And then to get the other one, discard X. To get equality. Right? Good. We proved that squash entanglement is convex, right? So, using convexity, take a convex combination of these. That's what we're considering right here. It's one of the desired things to prove. So from the convexity, we can use this equality. And now the convexity. If we take a convex combination of these tau x's, that's this thing, rho xa thing. Right? So using convexity, we get this. Right? And similarly, here we implicitly, we appended x and discarded it with respect to Alice. We can also do it with respect to Bob, because that's a local channel. Right? So using a similar argument, we get that, right? So we've shown this one is greater than this one, and it's greater than this one. So now we're going to show the reverse inequalities, and then we'll be able to conclude equality. All right? So to do this, we just use the confidence and the local channels. In fact, the dependent and discarding is a local channel. So now we'll prove the opposite. Okay. So to prove the opposite inequalities, we have to consider an arbitrary extension. We want to consider this squash entanglement. We have to consider an arbitrary extension of this state. So because the system X is classical, in an extension, the system X has to remain classical as well. Right? So we can argue that the extension state has to look like this. Where the probability distribution is the same, and each of these omega x's actually extend the rho ABX individual terms in the CQ state. Okay. And once we have that, we're kind of on our way. It's was this clear? Why this is the case? It has to do with the fact that the system X is classical. That limits the form, like, there's being an extension, you have to be consistent with the reduced state, right? And since the reduced state has this specialized form being classical quantum, to maintain that consistency, the only possible way that you could choose an extension is this way. Yeah,
What if you add like a maximum state on XC?
maximum mixed state of XE.
And you trace out E, you get the identity, right? That would be a classical.
Yeah.
That is also an extension.
We have to extend these three systems.
If you have X, E, A, B.
Right.
X and E is now an entangled. So basically, I don't understand the condition that X has to remain classical.
Wow. That is the plan. I'm trying to counter a good point. This X is correlated with this. Right, let's say. This is a good point that you're making. I want to think, we have 7 minutes I want to think about. I'm going to purify this. This is going to be a particular purification of rho X, right? Okay. And this will be a particular purification of rho X AB. X and X. That's so, we can get to other purifications by doing an isometry. This. Phi. Doing that with 5. And then this can, I think this is related to the point you're making. This can like mix up the classical register with the purifying system. I need to think about this offline. Let me finish the proof as it is, subject to this perhaps dubious claim. Okay. Okay, so you know what? I think this is wrong. This is supposed to be a particular extension. I think in my notes I wrote it wrong. The particular extension of rho x, yeah, has this form. Okay, but each of these omega x's will be an arbitrary extension of rho x AB. Okay? So yeah, we don't need an arbitrary extension. So let me just this. Okay, and then because it's a particular extension, we can apply the definition of squash entanglement to get this. I think we might be. Let me continue. Sorry. Okay, and then because this is convex combination and this X system is classical, and then do this. Then the next thing I wanted to use is the chain rule to write this as I X A B minus, sorry, this is now state omega. So that's again the chain rule. CMI is non-negative. Drop this. And I think we arrived at the point where I actually we do need to use the arbitrary extension. So anyway, that was going to be the final point that if this is an arbitrary extension, then this implies that inequality. The claim being that if this omega was an arbitrary extension, then you could do this. Right? So that needs to be rethought. My apologies. We kind of hit the time. The plan for the rest of the lecture was to talk about, I could just state one fact, that squash entanglement for a pure state, so for pure state psi degree, that is equal to the entropy of entanglement of psi, because the only way you can pick an extension of a pure system is as a product. So that is true. And then you just end up evaluating mutual information and you arrive at this conclusion. And so the plan after that was to actually prove the claim at the beginning that the stillable entanglement is less than squash entanglement. We don't really have time to do that. So, yeah, I mean, I need to think about that. Whether it's true, I thought, anyway. So I will see you on Monday. Okay.